The universe is a stage, and every so often, it puts on a performance so rare, so breathtaking, that if you blink, you might miss it forever. Picture this, a sky so alive with celestial fireworks that it feels like the cosmos is whispering secrets meant only for those who dare to look up. These aren't just ordinary astronomical events. They're once-in-a-lifetime spectacles, moments when the universe bends the rules and leaves us in sheer wonder. From planets aligning in perfect harmony to stars exploding in violent brilliance, these rare phenomena remind us how small we are, and yet how connected we are to something infinitely grander. Think about the last time you stood outside on a clear night staring at the stars. Maybe you spotted a shooting star, a fleeting streak of light that vanished as quickly as it appeared. Now imagine witnessing something even more extraordinary, a comet so bright it's visible in broad daylight, or a meteor storm so intense it looks like the sky is raining fire. These events don't happen every year or even every century. Some unfold only once every few thousand years, and if you're lucky enough to catch one, you're sharing a moment with ancestors who saw it centuries before you, and descendants who won't see it again for lifetimes to come. That's why we're here to explore 25 of the rarest, most awe-inspiring astronomical events you simply can't afford to miss. Whether it's a blood moon casting an eerie glow over the landscape or a planetary dance so precise it defies belief, each of these phenomena tells a story about the universe's endless creativity. Some will challenge everything we think we know about space and time. Others will leave you speechless, humbled by the sheer scale of it all. So buckle up, because we're about to embark on a journey through the most extraordinary sights the cosmos has to offer, events that will make you rethink your place in the stars. The universe is waiting. Are you ready to look up? The night of December 21st, 2020 wasn't just any winter solstice. It was the moment two giants of our solar system staged a reunion so rare. The last time they appeared this close, medieval astronomers were the ones gazing up in wonder. Jupiter and Saturn, the gas giants we often spot as bright dots in the night sky, drew nearer to each other than they had in nearly 8 centuries, creating what many called the Christmas star. This wasn't just a celestial coincidence, it was a masterpiece of orbital mechanics. Conjunctions happen when planets align along the same line of sight from Earth, but this event was special. Normally, Jupiter overtakes Saturn in the sky every 20 years, but their orbits rarely bring them this close, just 1/10 of a degree apart, or roughly the width of a dime held at arm's length. Cultures across history have interpreted these cosmic meetups as omens or celestial messages. The famed astronomer Johannes Kepler even theorized that a similar conjunction might have been the biblical Star of Bethlehem. Fast forward to 2020, and the world watched in awe as the planets nearly merged into a single glowing point, visible even to the naked eye. The best part, you didn't need a telescope to witness it, just a clear southwestern horizon right after sunset. Social media lit up with photos of the duo shining like a double star, a reminder that the universe occasionally hands us front row tickets to its grandest shows. But what does it take to spot the next great conjunction? While the two planets won't come this close again until the year 2840, smaller alignments happen every couple of decades. The key is timing and location. Look for Jupiter's steady glow and Saturn's golden hue low in the twilight sky, usually in December or January. Apps and star maps can help pinpoint the exact dates, but sometimes the old-fashioned way, just stepping outside and looking up, works best. After all, these slow-motion celestial dances remind us that the universe operates on a timescale far beyond our own, weaving moments of wonder into the fabric of time itself. On June 5, 2012, the world witnessed a celestial ballet so rare that if you missed it, you'd have to wait another 105 years for the next performance, the transit of Venus. This wasn't just a planet passing in front of the sun. It was a cosmic alignment that helped humanity crack one of the universe's greatest mysteries, the scale of our solar system. Picture Venus, a tiny black dot inching across the sun's fiery disk, a sight so precise and fleeting that early astronomers risked their lives to observe it. Expeditions set sail across oceans, braving storms and disease, just to catch a few hours of this event. Why? Because these transits held the key to measuring the distance between Earth and the Sun, a number that would redefine our understanding of the cosmos. The math behind it is as elegant as the event itself. By observing Venus's path from different points on Earth, astronomers could use parallax, the slight shift in perspective, to triangulate the distance to the Sun. The 18th century scientist Edmund Halley of comet fame first proposed this method, but it took two global efforts during the transits of 1761 and 1769 to put it into practice. Teams scattered from Siberia to Tahiti, their clocks synchronized, their telescopes trained on the sky. The data they collected finally gave us the astronomical unit, the yardstick for our solar system. Fast forward to 2012, and the transit was no less monumental. Modern telescopes captured Venus's silhouette with stunning clarity, while amateur astronomers projected the image onto paper, sharing the moment with crowds gathered in parks and observatories. But the real magic lay in the rarity. These transits come in pairs, 8 years apart, separated by gaps of over a century. The last duo happened in 1874 and 1882. The next won't occur until December 10th and 11th, 2117. That's right. If you were lucky enough to see the 2012 transit, you've already lived through half of this century's opportunities. So what makes this event so captivating? It's not just the science or the scarcity, it's the connection across time. When you watched Venus glide across the Sun in 2012, you were part of the same story that inspired Halley, Cook, and countless others who turned their eyes skyward, chasing answers in the stars. And for those who missed it, mark your calendars for 2117 because some celestial performances are worth waiting a lifetime to see. January 21st, 2019 gave us a celestial trifecta so striking that even seasoned astronomers paused to marvel, the super blood wolf moon. This wasn't just any lunar eclipse, it was a rare convergence of three extraordinary phenomena, each one dramatic enough on its own. First, the supermoon effect made our lunar neighbor appear 14% larger and 30% brighter than usual as it reached the closest point in its elliptical orbit around Earth. Then, as Earth's shadow crept across the moon's surface, sunlight filtering through our planet's atmosphere painted it a deep, eerie red, the blood moon effect. And to crown it all, this cosmic spectacle unfolded during the first full moon of January, traditionally known as the wolf moon, a name echoing centuries of folklore and winter tales. The science behind this event is as captivating as its name. A supermoon occurs because the moon's orbit isn't a perfect circle, it's slightly oval, with a far point called the apogee and a near point, the perigee. When a full moon coincides with perigee, it looms larger in our sky, its craters and seas thrown into sharp relief. But the real show began as Earth slid between the sun and the moon, casting our shadow across its surface. Unlike a solar eclipse where darkness falls suddenly, a lunar eclipse unfolds in slow motion, with the moon passing through Earth's penumbra and umbra, dimming before glowing crimson. That red hue, its sunlight bent by Earth's atmosphere, the same physics that turns our sunset scarlet, projected onto the lunar surface like a celestial spotlight. Indigenous cultures and early settlers wove rich stories around these events. The wolf moon, for instance, comes from Algonquin tribes who associated January's howling winds with hungry wolves prowling winter villages. Meanwhile, ancient Mesopotamians saw blood moons as omens, while Incan astronomers interpreted them as a jaguar attacking the moon, demanding rituals to ward off chaos. Even today, the sight of a coppery moon hanging low on the horizon stirs something primal, a reminder that our ancestors watched these same skies with equal parts awe and trepidation. What made the 2019 event particularly special was its visibility. Unlike planetary alignments requiring perfect timing or solar eclipses limited to narrow paths, this lunar eclipse was visible across the Americas, Europe, and Africa. All you needed was a clear sky, no telescopes, no filters. Families bundled up in blankets, photographers set up tripods in backyards, and social media feeds flooded with images of the rust-colored moon. It was astronomy at its most democratic, a shared moment of wonder under a transformed sky. While supermoons happen a few times a year and lunar eclipses aren't exactly rare, the combination of all three, supermoon, blood moon, and wolf moon, is a celestial recipe that won't repeat for decades. The next lunar eclipse with this exact trio of traits won't grace our skies until 2068. But here's the silver lining: even without the full trifecta, each component offers its own magic. A blood moon alone is worth setting an alarm for, and a supermoon turns an ordinary night into a photographer's dream. The universe may save its grandest performances for rare dates, but it never stops offering encores. Halley's Comet isn't just a celestial visitor. It's a time traveler, a cosmic clock that ticks once every 76 years, linking generations across history. When it streaks through our skies in 2061, it'll carry with it the weight of millennia, from ancient Babylonian astronomers who recorded its movements on clay tablets to the crowds of 1910 who panicked, convinced its tail carried deadly gases. Few astronomical events have woven themselves so deeply into human culture. The Bayeux Tapestry, that famous medieval embroidery depicting the Norman conquest of England, even immortalized its appearance in 1066 as an omen hanging over the Battle of Hastings. King Harold's soldiers supposedly saw it as a portent of doom, and in a way they weren't wrong. What makes Halley's Comet so special isn't just its regularity but its unpredictability. Unlike the steady rhythm of planets, comets are cosmic wildcards, their tails shaped by solar winds, their brightness impossible to forecast. In 1986, its last visit, disappointed stargazers complained it was underwhelming, a faint smudge in light-polluted skies. But go back to 1910, and newspapers described it as a blazing spectacle, visible even in daylight, its tail stretching nearly halfway across the heavens. The difference: Earth's position during each flyby. In 2061, we'll be on the sunny side of the comet, with its tail fully illuminated and potentially more dramatic. So how can you prepare for this once or twice in a lifetime event? First, mark your calendar. Late July 2061 will be prime viewing, with the comet brightest as it swings closest to the sun. Unlike fleeting meteors, Halley's Comet lingers for weeks, giving you plenty of chances to spot it. Find a dark sky away from city lights. A rural backyard or a hilltop will do. No fancy equipment is needed. Binoculars will reveal its fuzzy coma and tail, though a small telescope might show the delicate structure of its ion tail, a glowing blue streak of charged particles. But the real magic of Halley's Comet lies in its legacy. When you see it in 2061, you'll be sharing the sky with Mark Twain, who was born under its glow in 1835 and died as it returned in 1910, just as he predicted. You'll be part of a chain that includes Einstein, Shakespeare, and maybe even your great-grandchildren. That's the wonder of this celestial nomad. It doesn't just cross space. It connects us across time. On August 21, 2017, a shadow raced across America at nearly 1,700 miles per hour, not from storm clouds, but from the moon itself, casting a ribbon of daytime darkness from Oregon to South Carolina. This was the Great American Eclipse, the first total solar eclipse to sweep coast to coast in 99 years, and it transformed ordinary towns into pilgrimage sites for millions. The path of totality, that narrow 60 to 70 mile wide corridor where the moon completely blocked the sun, became hallowed ground for astronomers and casual skywatchers alike. People parked cars on highways, crowded into fields, and even got married under the sudden twilight, all to witness those precious 2.5 minutes when day turned to night in the blink of an eye. What made this eclipse so unforgettable wasn't just the rarity, it was the theater of it all. As the moon's silhouette slid over the sun, the temperature dropped 15 degrees in minutes. Birds fell silent, confused by the false dusk, while crickets began chirping as if evening had arrived. Streetlights flickered on, and the sun's corona, that wispy halo of plasma normally invisible to the naked eye, blazed around the blackened moon like a ring of molten silver. Those outside the path of totality saw only a partial eclipse still striking, but nowhere near as transformative. Inside the path, the difference was cosmic. You could peel off your eclipse glasses during totality and stare directly at the sky, where Venus and Jupiter emerged like unexpected guests at a celestial party. Scientists had been preparing for this moment for decades. NASA launched high-altitude balloons to study the sun's atmosphere, while biologists documented how animals reacted to the sudden darkness. Meanwhile, ordinary people became amateur astronomers, crafting pinhole projectors from cereal boxes or welding masks to safely view the spectacle. The event even bridged political divides. Lawmakers in Washington, D.C. paused debates to stand on the Capitol steps, sharing eclipse glasses like kids at a planetarium. But here's the thrilling part. If you missed the 2017 eclipse, the universe is giving you a second chance. On April 8, 2024, another total solar eclipse will carve a path from Texas to Maine, and this one promises to be even more dramatic. Why? 3 reasons. First, totality will last up to 4 minutes and 28 seconds, nearly double the 2017 duration, thanks to the moon's closer proximity to Earth. Second, the path cuts through more major cities, putting millions more people within easy reach of totality. And third, the sun will be near solar maximum in 2024, meaning its corona will likely appear larger and more structured, with streaming loops of plasma visible to the naked eye. Planning for the 2024 eclipse has already begun. Hotels along the path are booking up years in advance, and astronomers warn against waiting until the last minute to secure viewing spots. The lesson from 2017 is clear. Totality isn't just something you see, it's something you feel. It's the collective gasp of a crowd when the last sliver of sunlight vanishes. It's the sudden chill in the air, the hushed awe, the primal thrill of standing in the moon's shadow. Whether you're a seasoned eclipse chaser or a first-time skywatcher, mark your calendar for April 8, 2024. The universe doesn't just put on a show, it crafts an experience you'll carry with you long after the sun returns. The night of November 12, 1833, wasn't just a meteor shower, it was a celestial hurricane. Across North America, people woke to a sky ablaze with streaks of light, so dense and brilliant that many mistook it for the end of the world. Eyewitnesses reported seeing up to 100,000 meteors per hour, a spectacle so intense that some described it as stars falling like snowflakes. This was the Leonid meteor storm, a cosmic event so rare and violent it reshaped our understanding of what's possible in the night sky. Unlike typical meteor showers where you might spot a dozen or so streaks an hour, storms like this one turn the atmosphere into a canvas of fire, with meteors appearing faster than you can count them. The Leonids owe their fury to Comet Tempel-Tuttle, a cosmic nomad that swings by the sun every 33 years, shedding trails of dust and debris. When Earth plows through one of these dense debris fields, the particles no larger than grains of sand burn up in our atmosphere, creating the streaks we call meteors. Most years, the Leonids deliver a modest show, maybe 15 meteors per hour. But every few decades, when Earth crosses a particularly rich filament of comet dust, the sky erupts. The 1833 storm was so legendary that it inspired songs, sermons, and even slave narratives, with Frederick Douglass later recalling how his community interpreted the event as a divine omen. What makes meteor storms so unpredictable is the chaotic nature of comet debris. Unlike planets with orderly orbits, comets leave uneven trails of material scattered by solar winds and planetary gravity. Astronomers now know that Tempel-Tuttle's most recent close pass in 1998 set the stage for another Leonid outburst in 2001. While it didn't rival the 1833 storm, observers in Europe and Asia still reported thousands of meteors per hour, a reminder that these cosmic fireworks are very much a living phenomenon, not just a relic of history. If you're hoping to witness the next great Leonid storm, patience is key. The best bets are years when Tempel-Tuttle returns, with the next perihelion expected in 2031. But here's the catch: not every return produces a storm. The debris has to be just right, and Earth has to plow through the densest part of the stream. Your best strategy: mark mid-November on your calendar every year, find a dark spot far from city lights, and look toward the constellation Leo after midnight. Even in off years, the Leonids can surprise you with brief surges of activity. And when the next storm comes, you'll want a front row seat, because few things in astronomy match the raw, primal thrill of a sky on fire. For those who missed the great storms of the past, take heart. Meteor science has come a long way since 1833. Today, satellites and radar track debris streams in real time, giving us days, sometimes hours, of warning when a potential outburst is coming. Apps and astronomy websites will light up with alerts when conditions are ripe. All you need is a clear sky, a blanket, and the willingness to stay up late. After all, the universe doesn't keep a schedule. It saves its greatest shows for those who dare to watch and wait. One summer morning in 1972, the sky over the American West turned into a stage for one of the most audacious meteor displays ever recorded. It was August 10th, just after 8 o'clock, when a basketball-sized chunk of cosmic debris traveling at a staggering 9 miles per second slammed into Earth's atmosphere over Utah. What happened next wasn't just another shooting star. This was a daylight fireball, a meteor so blindingly bright it rivaled the sun, casting sharp shadows across the ground as it streaked northward. Eyewitnesses from Salt Lake City to Calgary described a searing white light trailing thick black smoke, some even hearing a sonic boom as the rock fragmented 50 miles above Montana. For nearly 100 seconds, this celestial intruder held the attention of millions, cutting a path so vivid it left reports of singed retinas and startled livestock in its wake. Daylight fireballs are among the rarest meteor events you'll ever witness. Most meteors burn up unnoticed, visible only under the cloak of night. But when a particularly large or fast-moving object enters the atmosphere, especially one made of dense iron or stony material, it can outshine the midday sun. The 1972 event, later nicknamed the Great Daylight Fireball, was exceptional not just for its brilliance but for its survival. Unlike most space rocks that disintegrate completely, this one skipped across the upper atmosphere like a stone on water, losing enough speed to potentially return to space. Calculations suggest it grazed Earth at an angle of just 15 degrees, briefly becoming a temporary mini-moon before vanishing back into the cosmos. No fragments reached the ground, but its fiery farewell left a legacy in satellite data and newspaper headlines. Recent years have gifted us a handful of comparable spectacles. In 2013, a house-sized asteroid exploded over Chelyabinsk, Russia, with the force of 30 Hiroshima bombs, its shockwave shattering windows and injuring over 1,000 people. Then in 2020, a daylight fireball lit up skies from Vermont to Ontario, captured by doorbell cameras and traffic cams alike. What makes these events so gripping isn't just their rarity, it's their unpredictability. Unlike eclipses or comet flybys, meteor strikes give no warning. Their cosmic lightning strikes brief, violent, and utterly uncontrollable. For those hoping to spot a daylight fireball, the odds are slim but not impossible. Your best chance comes during major meteor showers like the Perseids or Geminids, when Earth plows through denser debris fields. But the real lesson of 1972 is this: keep your eyes on the sky even when the sun is high. The universe doesn't reserve its greatest shows for nighttime. Sometimes it rolls out the fireworks when we least expect them, turning an ordinary afternoon into a front-row seat for celestial drama. While Venus steals the show with its dramatic, once-in-a-century transits, its tiny neighbor Mercury offers a more subtle, but no less fascinating celestial performance. On November 8, 2004, skywatchers witnessed a rare alignment: Mercury, the solar system's smallest planet, inching across the face of the Sun like a microscopic shadow. Unlike Venus's slow 6-hour march, Mercury's transit lasted just under 5 hours, its diminutive size making it a challenge to spot without magnification. But what this event lacked in grandeur, it made up for in frequency and scientific value. While Venus transits come in pairs separated by over a century, Mercury treats us to 13 or 14 crossings every 100 years, each one a reminder of how precisely the planets move in their cosmic dance. The key difference lies in orbital geometry. Mercury circles the Sun every 88 days, far closer than Venus, which means it crosses between Earth and the Sun more often. But here's the catch: Mercury's orbit is tilted relative to ours, so most of the time, it passes just above or below the Sun from our perspective. Only when Earth and Mercury align perfectly at points called nodes do we see a transit. These conditions create predictable patterns. Transits tend to cluster in early May or mid-November, with November events being slightly more common due to Mercury's position. The 2004 transit fell into this November window, with observers armed with solar telescopes capturing the planet as a crisp black dot against the Sun's boiling surface. Scientists treasure these events for reasons that go far beyond Mercury itself. Transits are our most powerful tool for discovering and studying planets orbiting distant stars, exoplanets. When a world like Mercury passes in front of the Sun, it blocks a tiny fraction of sunlight, and modern instruments can detect similar dips around other stars. The 2004 transit even served as a dress rehearsal for exoplanet research. Astronomers used it to test techniques for measuring atmospheric composition, since Mercury's ultra-thin exosphere subtly filters sunlight. Fast forward to today, and these same methods have identified thousands of exoplanets, some with water vapor or methane in their atmospheres, potential hints of life. Mark your calendars for November 13, 2032, the next time Mercury will grace the Sun's disk. This transit will favor observers in Australia, the Pacific, and the Americas, with the entire event visible from parts of Western South America. But even if you're outside the ideal viewing zone, modern technology brings these once inaccessible events to your screen. Space agencies like NASA often live-stream transits with high-resolution telescopes, offering close-ups of Mercury's silhouette against solar prominences and sunspots. And here's a pro tip: unlike Venus, which appears large enough to see with proper eye protection as a distinct black dot, Mercury requires at least a telescope with a solar filter to appreciate its tiny, perfect circle. The beauty of Mercury's transits lies in their duality. They're both a backyard astronomy challenge and a cornerstone of cutting-edge astrophysics. Each one is a reminder that the same celestial mechanics governing our solar system also shape the search for worlds beyond it. And while they may not have the mythic rarity of Venus's crossings, Mercury's frequent visits offer something equally precious: regular invitations to witness the clockwork precision of the universe, one tiny shadow at a time. The night of February 23, 1987, crackled with something electric, though no one knew it yet. In a small observatory in Chile, an astronomer named Shouldnt was reviewing photographic plates of the Large Magellanic Cloud, a satellite galaxy of our Milky Way. Then he saw it, a brilliant new star where none had been before. Within hours, telescopes around the world swiveled toward the southern sky, confirming what hadn't happened in nearly 400 years, a supernova visible to the naked eye. SN 1987 wasn't just a scientific jackpot, it was a cosmic wake-up call, a reminder that stars die violently, and when they do, the universe puts on a light show that can outshine entire galaxies. This wasn't just any stellar explosion. The doomed star Sanjalik 69 degrees 202 had been a blue supergiant 20 times the mass of our Sun, and its death throes defied expectations. Most supernova models predicted red supergiants would explode, but here was a blue one rewriting textbooks in real time. For months, the supernova blazed with the intensity of 100 million suns, so bright it could be seen from light years away without a telescope. Amateur stargazers in Australia and New Zealand reported spotting it from backyards, while astronomers scrambled to capture every possible wavelength of light from radio waves to X-rays. What made SN 1987 a revolutionary wasn't just its spectacle, it was the treasure trove of data. For the first time, scientists detected neutrinos, ghostly subatomic particles produced in the supernova's core, hours before the light reached Earth. These neutrinos, picked up by detectors in Japan and the United States, confirmed theories about how stars collapse. Meanwhile, the Hubble Space Telescope later captured something even more extraordinary, a glowing ring of gas around the explosion, lit up by the shockwave. This pearl necklace of hotspots, as astronomers dubbed it, revealed secrets about the star's final years, including violent winds that had sculpted its surroundings long before it died. But here's the thrilling part: the next nearby supernova could happen any night. Betelgeuse, the red supergiant in Orion's shoulder, has been dimming and brightening erratically, sparking speculation it might be on the verge of exploding. If it does, it would be the brightest supernova in recorded history, visible even in daylight for weeks. Then there's Eta Carinii, a volatile binary system in the southern sky, which could unleash a hypernova, a supernova on steroids. The catch: predicting these events is nearly impossible. Stars give few clear warnings before they go supernova, and our galaxy is overdue for one. Statistically, a star explodes in the Milky Way every 50 years or so, but the last one visible from Earth was Kepler's supernova in 1604, hidden behind interstellar dust. Modern telescopes and neutrino detectors mean the next one won't slip by unnoticed. When it happens, it'll be a global event, astronomers and amateurs alike staring at the same patch of sky, united by the rare privilege of witnessing a star's final act. So keep looking up. Supernovas aren't just fireworks, they're the universe's way of recycling. The iron in your blood, the calcium in your bones, all forged in stellar explosions like SN 1987A. Every time you glance at the night sky, remember, you're made of star stuff, and somewhere out there, another star is preparing to scatter its ashes across the cosmos, waiting for the perfect moment to blaze into history. On April 13, 2029, Earth will host an uninvited guest, an asteroid the size of the Empire State Building, hurtling past us at nearly 25,000 miles per hour. This is Apophis, named after the Egyptian god of chaos, and for 17 tense years after its discovery in 2004, scientists thought it might actually live up to its ominous name. Early calculations suggested a small but real chance it could strike Earth in 2029, sparking a meteor frenzy and doomsday prophecies. But here's the twist: Apophis isn't going to hit us. Instead, it's giving humanity a front-row seat to one of the closest asteroid flybys in recorded history, passing just 19,000 miles above our heads. That's closer than some weather satellites, close enough for observers in parts of Asia and Africa to potentially see it streak across the night sky with nothing more than binoculars. What makes this event so extraordinary isn't just the near miss, it's the science bonanza it represents. Apophis will swing so close that Earth's gravity will visibly alter its orbit, bending its path like a cosmic slingshot. Ground-based telescopes will map its surface in unprecedented detail, while radar systems like NASA's Goldstone antenna will ping it with radio waves, measuring its spin and composition down to the meter. This isn't just academic curiosity. Apophis is a rehearsal for planetary defense. By studying how its trajectory shifts during this encounter, astronomers can refine their ability to predict future threats. The data collected could one day save civilization if or when a truly hazardous asteroid heads our way. The doomsday hype, though, couldn't be further from reality. Apophis's initial scare came from early observations with large margins of error. As tracking improved thanks to radar and space-based telescopes like NEOWISE, the risk dropped to zero. By 2021, NASA had officially ruled out any impact for at least the next century. Instead of Armageddon, we're getting a masterclass in celestial mechanics. The asteroid's 2029 flyby will showcase gravity's invisible hand at work, tweaking Apophis's orbit so dramatically that future close approaches won't happen again for centuries. For skywatchers, the real magic will be in the details. Under dark skies, Apophis could reach magnitude 3, about as bright as the stars in the Little Dipper, moving fast enough to see its motion in real time. It'll first appear near the constellation Cancer, racing westward across the sky over several hours. Amateur astronomers with small telescopes might even resolve its elongated shape, a tumbling mountain of rock and metal reflecting sunlight. But the best views will come from live streams. Observatories worldwide will train their lenses on the event, offering close-ups of this cosmic visitor as it makes its record-breaking pass. What's perhaps most humbling is the timeline. Apophis won't come this close again until the year 2066, and even then, it'll be much farther away. This is a once-in-a-lifetime opportunity, not just for scientists, but for anyone who's ever looked up and wondered about our place in the solar system. When you watch Apophis glide past in 2029, you'll be witnessing something far rarer than a solar eclipse or a planetary alignment. You'll see proof that space isn't empty, that Earth exists in a celestial shooting gallery, and that humanity is finally learning to keep score. In August 2003, Mars didn't just shine in the night sky, it dominated it. For the first time in 60,000 years, the red planet swung closer to Earth than it had since the dawn of human civilization, glowing like a fiery ember against the stars. At just 34.6 million miles away, Mars appeared 6 times brighter than usual, its rusty disk so large that even backyard telescopes revealed sprawling canyons, towering volcanoes, and swirling dust storms. This wasn't just an astronomical event, it was a moment of connection, a chance to witness our planetary neighbor in staggering detail, as if the universe had dialed Mars up to maximum clarity. What made this close approach so historic wasn't just the distance, it was the timing. Mars reaches opposition, its closest point to Earth, roughly every 26 months, but not all oppositions are equal. The planet's elliptical orbit means some bring it dramatically nearer than others. The 2003 event coincided with perihelic opposition, when Mars was also at its closest to the Sun, creating a perfect celestial alignment. The result, a view of Mars so vivid that amateur astronomers could spot the southern polar cap shrinking under the summer sun, while global dust storms painted the planet's face in shifting ochre hues. Future oppositions offer their own magic, though none will match 2003's record-breaking proximity until the year 22,857. The next notable close approach comes in 2035, when Mars will drift within 35.8 million miles. Still a spectacular sight, with surface features like Syrtis Major and Hellas Basin easily visible through modest telescopes. But the real key to observing Mars lies in patience and preparation. During opposition season, the planet rises at sunset and stays bright all night, but atmospheric turbulence can blur details. Wait until Mars climbs high in the sky, usually around midnight when Earth's distorting air is thinnest. A steady night with good seeing conditions, when stars twinkle less, can transform a fuzzy orange blob into a world of sharp contrasts and intricate terrain. For those eager to chase dust storms or track seasonal changes, Mars rewards regular observation. The planet's thin atmosphere creates weather patterns that shift over weeks, with dust devils spiraling across plains and frost creeping over polar regions. In 2018, a planet-wide dust storm engulfed Mars, obscuring even its tallest peaks for months, a reminder that this isn't a static world. Catching these events requires persistence, but the payoff is immense. You're not just looking at a dot in the sky. You're watching a dynamic, alien landscape unfold in real time. While 2003's close approach remains unmatched, every opposition offers a fresh perspective. Some years favor northern hemisphere features, others highlight the south. Sometimes Mars flaunts its icy poles, other times it vanishes beneath a blanket of dust. The red planet is a shapeshifter, and that's what makes it endlessly fascinating. Whether you're sketching its surface details through a telescope or simply marveling at its brilliance with the naked eye, Mars invites you to see the solar system not as a static map, but as a living, breathing neighborhood, one where distances shrink and worlds reveal themselves, if only for a little while. In July 1994, humanity witnessed something unprecedented, a cosmic demolition derby unfolding 500 million miles away. Comet Shoemaker-Levy 9, a fractured remnant of what was once a single icy body, plunged into Jupiter's atmosphere in a series of violent impacts over 6 harrowing days. 21 fragments, some over a mile wide, slammed into Jupiter's cloud tops at 40 miles per second, each explosion releasing energy equivalent to millions of nuclear bombs. The scars left behind were staggering, dark, Earth-sized bruises in Jupiter's atmosphere, some lingering for months. For the first time in history, we weren't just theorizing about celestial collisions. We were watching one happen in real time, and it forever changed how we view our place in the solar system. What made this event so extraordinary wasn't just the spectacle, it was the sheer improbability of catching it at all. The comet had been torn apart by Jupiter's gravity 2 years earlier, captured like prey in a planetary snare. Astronomers Carolyn and Eugene Shoemaker, along with David Levy, spotted the fractured comet in 1993, its train of debris resembling a string of luminous pearls. By the time scientists realized these fragments were on a collision course, the world's telescopes were already trained on Jupiter, waiting for the show to begin. The Hubble Space Telescope, still in its infancy, captured every moment, revealing plumes of superheated gas rising 2,000 miles above Jupiter's clouds, towering fireballs visible even against the planet's vast disk. The aftermath of Shoemaker-Levy 9 wasn't just a scientific curiosity, it was a wake-up call. Before 1994, the idea of asteroids or comets striking planets felt like the stuff of disaster movies. Suddenly, it was undeniable physics. Jupiter, with its massive gravity, acts as a cosmic vacuum cleaner, drawing in wayward objects that might otherwise threaten inner planets like Earth. The comet's impacts proved that these collisions aren't relics of the ancient past, they're ongoing, inevitable events. If Jupiter hadn't intercepted Shoemaker-Levy 9, some fragments could have wandered into the inner solar system, posing a potential threat. This realization sparked a seismic shift in planetary defense. NASA's Near-Earth Object Program, tasked with tracking potentially hazardous asteroids, gained newfound urgency. Telescopes like Pan-STARRS in Hawaii and the Catalina Sky Survey in Arizona began scanning the skies in earnest, cataloging thousands of near-Earth objects. The data was chilling. We share our cosmic neighborhood with over 20,000 asteroids large enough to cause regional devastation if they struck Earth. Shoemaker-Levy 9's legacy lives on in missions like DART, which successfully nudged an asteroid off course in 2022, proving we might one day deflect a real threat. For amateur astronomers, the impacts offered something equally profound, proof that the universe is alive with violence and beauty. Though no Earth-based telescope could see the actual explosions, they occurred on Jupiter's far side. The planet's rapid rotation brought the damage into view within hours. Observers reported dark smudges so distinct they could be seen through modest backyard telescopes. The event democratized astronomy, turning anyone with a lens into a witness to cosmic history. Today, Shoemaker-Levy 9 serves as both a warning and an inspiration. It taught us that planetary impacts aren't hypothetical, they're etched into the fabric of our solar system. Jupiter's scars have faded, but their lesson remains. The sky isn't just a canvas of quiet stars. It's a dynamic, sometimes dangerous place, and for the first time, we're learning to read its rhythms and defend ourselves against its storms. The morning of February 15, 2013, began like any other in the Russian city of Chelyabinsk until a fireball brighter than the sun split the sky. Traveling at 42,000 miles per hour, the 55-foot-wide asteroid exploded 14 miles above ground with the force of 30 Hiroshima bombs. The shockwave shattered windows across 6 cities, sent debris raining onto frozen lakes, and injured more than 1,600 people, many cut by flying glass as they rushed to watch the blazing trail. Security cameras captured the moment. Classrooms and offices became disaster zones, ceiling tiles collapsing, car alarms wailing, people screaming as the sky turned white. This wasn't just another shooting star. It was the largest recorded meteor strike to hit a populated area in over a century, a visceral reminder that space doesn't care about human schedules. What made the Chelyabinsk meteor so unnerving was its stealth. Unlike comets that announced their approach over months, this asteroid came from the direction of the sun, invisible to telescopes until it was already burning through the atmosphere. By the time anyone saw it, the rock was less than a second from exploding. The event exposed a gaping hole in our planetary defense network. We're effectively blind to objects approaching from the sun's glare. But Chelyabinsk also delivered an unexpected gift: thousands of dashcam videos. Russia's ubiquitous traffic cameras provided the most detailed meteor footage in history, allowing scientists to reconstruct everything from its angle of entry to the precise energy of its explosion. The aftermath sparked a global reckoning. NASA's Near-Earth Object Program, which had been tracking larger asteroids for decades, suddenly faced pressure to find smaller, Chelyabinsk-sized threats. Today, projects like Atlas in Hawaii scan the sky nightly for faint streaks of motion, while the European Space Agency's Fly-Eye telescope uses a compound lens designed to spot fast-moving objects. Even amateur astronomers contribute, with networks like the All-Sky Fireball Network crowdsourcing meteor detections. The goal: catching the next city killer before it catches us. Yet for all our technology, the universe still holds surprises. In 2019, a 100-foot asteroid named 2019 OK zipped past Earth at 40,000 miles, only spotted days before its closest approach. And in 2023, a truck-sized asteroid burned up over France just hours after discovery, its fragments recovered in a rural field. These near misses aren't failures, they're proof that the solar system is a busy, unpredictable place. The lesson of Chelyabinsk isn't fear, it's preparedness. Thanks to that fiery wake-up call, we're now building telescopes on the moon to peer into the sun's blind spot and testing deflection missions like DART. The next time a big rock heads our way, we might not just watch it coming, we could stop it. For weeks in July 2020, the night sky hosted a visitor so brilliant it turned casual stargazers into comet chasers. Comet NEOWISE. This icy traveler, officially named C2020F3, became the brightest comet visible from Earth since Hale-Bopp graced our skies in 1997. Its dual tails stretching like celestial brushstrokes across the pre-dawn and evening hours. Unlike fleeting meteors or brief lunar eclipses, NEOWISE lingered, offering nightly shows that spanned continents. From suburban backyards to remote mountaintops, people pointed cameras and binoculars skyward, capturing a rare cosmic performance that hadn't been seen in a generation. What made NEOWISE extraordinary wasn't just its brightness, it was its resilience. Most comets fizzle as they approach the sun, their ices vaporizing too soon to create a spectacular display. But NEOWISE survived its closest solar pass in early July, emerging with a glowing nucleus and two distinct tails. A white dust tail curving behind it like a windsock and a faint blue ion tail pointing rigidly away from the sun. By mid-July, it had shifted to the evening sky, hovering near the Big Dipper, its tails growing longer each night. Social media flooded with images, some showing the comet above city skylines, others framing it against mountain ranges or lakes, all united by the singular thrill of seeing a piece of the solar system's primordial past blaze overhead. Photographing NEOWISE became a global pastime, and the lessons learned apply to future comets. The key to a great comet shot lies in three elements: darkness, stability, and patience. Find a location far from city lights, ideally with an unobstructed northwest horizon for evening viewing. Use a DSLR or mirrorless camera on a tripod, with exposures between 5 and 15 seconds to avoid star trails. Wide-angle lenses captured NEOWISE sweeping tails, while zoom lenses revealed the delicate structure of its nucleus. Many of the most stunning images came not from high-end gear but from smartphones mounted on tripods, proving that great comet photography is about technique as much as technology. The burning question now: when will the next great comet arrive? Astronomers track hundreds of comets yearly, but most are faint smudges visible only through telescopes. The truly dazzling ones like Hale-Bopp or NEOWISE are unpredictable. Some originate in the distant Oort cloud, a shell of icy debris at the solar system's edge, taking thousands of years to complete a single orbit. Others, like NEOWISE, are long-period comets with orbits measured in centuries. The next contender could be Comet Leonard, which brightened unexpectedly in 2021, or an undiscovered traveler still lurking beyond Neptune. What's certain is that comets like NEOWISE bridge the gap between science and wonder. They're frozen relics from the solar system's birth, carrying clues about Earth's water and organic molecules. Yet they're also cosmic artists, painting the sky with tales that shift daily, responding to solar winds like celestial weather vanes. NEOWISE reminded us that space isn't just a static backdrop. It's a dynamic stage where ancient icebergs occasionally step into the spotlight. So keep your cameras ready and your eyes on the horizon. The next great comet is out there, drifting in the dark, waiting for its moment to ignite the sky. On September 1st, 1859, the skies erupted in a light show so intense that miners in the Rocky Mountains woke up thinking it was dawn at 1 in the morning. Gold Rush prospectors cooked breakfast by the eerie glow, while in Cuba and Jamaica, crowds gasped at curtains of crimson and emerald rippling overhead. This wasn't just a spectacular aurora, it was the Carrington event, the most violent solar storm ever recorded. A geomagnetic hurricane so powerful it set telegraph offices on fire and sent sparks leaping from operators' hands. The cause, a colossal sunspot visible even to the naked eye through smoked glass, had unleashed twin solar flares directly at Earth. When the charged particles slammed into our atmosphere, they supercharged the planet's magnetic field, turning night into surreal day across continents. What makes the Carrington event so chilling isn't just its historical drama. It's the stark reality that our modern world is far more vulnerable. In 1859, the worst damage was a few fried telegraph lines. Today, a storm of equal magnitude could collapse power grids, cripple satellites, and knock out global communications for months. Think about the cascading chaos: no GPS for shipping, no electronic payments, no way to restart downed transformers without months-long manufacturing delays. A 2013 study estimated the cost of a Carrington-level event at up to $2 trillion, 20 times worse than Hurricane Katrina. with recovery taking years, not weeks. Yet for all our fears, the Carrington event also represents a turning point in science. Before 1859, few connected auroras to the sun. But when British astronomer Richard Carrington sketched the sunspot that spawned the storm and later linked it to the geomagnetic chaos, he birthed the field of space weather forecasting. Today, satellites like NASA's Solar Dynamics Observatory monitor the sun 24/7, while NOAA's Space Weather Prediction Center issues alerts like hurricane warnings. Scientists now know solar storms follow an 11-year cycle, with the next peak expected around 2025. The race to predict the next big one is more urgent than ever. Projects like the Parker Solar Probe dive closer to the sun than any spacecraft before, tasting the solar wind where it's born. Meanwhile, engineers harden power grids with fail-safes inspired by the Carrington event's lessons. Some countries, like the UK, have even stockpiled spare transformers underground, but the truth remains, we're still at the sun's mercy. The next monster storm could come tomorrow, or not for another century. For now, the Carrington event stands as both a warning and a wonder. It reminds us that the same forces painting the sky with unearthly light could also plunge our wired world into darkness. Yet it also proves humanity's knack for turning disasters into discovery. When that next great storm comes, whether it fries our gadgets or merely gifts us with auroras over Miami, one thing's certain: we'll be watching the sun more closely than ever. Most meteor showers follow a predictable script. You can circle their peak dates on your calendar years in advance, but every so often the universe throws us a curveball. On the night of November 21, 2001, skywatchers across Europe and North America witnessed one of the most dramatic meteor outbursts ever recorded, the Alpha Monocerotids. For less than an hour, the normally sleepy shower erupted with meteors streaking across the sky at a rate of nearly 1 per second, transforming an obscure annual event into a celestial fireworks show that left even veteran astronomers stunned. Unlike dependable performers like the Perseids or Geminids, this outburst wasn't caused by Earth plowing through the usual debris trail of a comet. Instead, it was the result of our planet colliding with a narrow, concentrated filament of dust, a cosmic thread so dense it turned the sky into a shooting gallery. The Alpha Monocerotids typically deliver just a handful of faint meteors each year, hardly worth setting an alarm for. But what makes this shower so fascinating is its potential for extreme outbursts when Earth crosses just the right part of the debris stream. Dutch meteor expert Peter Genniskens had predicted the 2001 event based on calculations of the parent comet's orbit, but no one expected the intensity of what unfolded. Observers described meteors appearing in rapid-fire succession, some leaving glowing persistent trains that lingered for seconds. The outburst was so concentrated that viewers outside its narrow activity window saw nothing, while those under the right patch of sky witnessed a once-in-a-lifetime display. This unpredictability is what sets meteor outbursts apart from their annual counterparts. Regular showers like the Perseids occur when Earth passes through broad, diffuse clouds of debris left by comets over centuries. Outbursts, however, happen when we intersect a fresh, tightly packed tendril of material, often released during a single recent pass of the parent comet. It's the difference between walking through a light mist and getting drenched by a fire hose. The 2001 Alpha Monocerotids outburst traced back to a strand of dust likely ejected by its mysterious parent object, possibly a long-period comet around 500 years earlier. The particles hadn't had time to disperse, creating a celestial bullseye that Earth hit dead-on for 20 thrilling minutes. For meteor hunters, outbursts like this are the holy grail. They demand vigilance and a willingness to brave cold November nights for a shower that might fizzle or explode. Veteran observers still talk about the 2001 event with reverence, comparing it to catching lightning in a bottle. The next potential outburst window opens around 2025, but predictions remain uncertain. That's the gamble with these cosmic wild cards. You never know when the universe will decide to paint the sky with fire. Between 2014 and 2015, a celestial phenomenon ignited both awe and anxiety, the so-called blood moon tetrad, a series of 4 consecutive total lunar eclipses, each bathed in eerie crimson light. This rare alignment only happens when the moon passes entirely into Earth's shadow 4 times in a row without any partial eclipses in between. The 2014 tetrad stood out not just for its striking visuals but for the frenzy it inspired. Some religious groups linked it to biblical prophecies, while doomsday theorists saw it as an omen of catastrophe. But behind the hype lay a fascinating interplay of orbital mechanics, one that reveals how predictable cosmic events can become cultural lightning rods. The science of tetrads hinges on geometry and timing. Lunar eclipses occur when Earth aligns directly between the Sun and Moon, casting a shadow that turns the moon coppery red as sunlight filters through our atmosphere. Normally, we see 2 or 3 lunar eclipses per year, but total eclipses are less common. A tetrad ramps up the rarity, 4 total eclipses in a row, each spaced about 6 months apart. What makes this possible is the moon's orbit. It's tilted about 5 degrees relative to Earth's path around the Sun, so most months, the moon dodges Earth's shadow entirely. But during periods when the alignment is just right, typically every few decades, the moon slips into the shadow zone repeatedly, creating a tetrad. Historically, tetrads have been anything but routine. The 20th century saw only 5, while the 21st will have 8, with the next one due in 2032 and 2033. Their frequency ebbs and flows due to subtle gravitational nudges from Jupiter and other planets, which tweak Earth's orbit over centuries. The 2014 tetrad was particularly notable because all 4 eclipses were visible from large parts of North America, a coincidence that amplified their cultural impact. Social media buzzed with images of the rust-colored moon hanging over cityscapes, while churches hosted blood moon viewing parties entwined with sermons. Astronomers, of course, saw a different story. For them, the tetrad was a chance to study Earth's atmosphere through lunar hues. The depth of red during a blood moon depends on airborne particles. Volcanic ash or pollution can darken the eclipse to a muddy brown, while clear skies produce a vivid copper tone. The 2014 eclipses varied strikingly, offering a snapshot of global atmospheric conditions. Scientists even used the events to calibrate instruments on lunar orbiting probes, since the moon's surface, bathed in Earth's filtered light, served as a natural calibration target. Yet the tetrad's legacy isn't just scientific. It underscored how easily celestial events become canvases for human narratives. Unlike random comets or meteor showers, tetrads unfold with ritualistic regularity, making them ripe for symbolism. The 2014 hype echoed past eclipses like the one said to have convinced Columbus to trick Jamaican natives into feeding his crew by predicting God's wrath, or the eclipses that terrified ancient Chinese dynasties, heralding the emperor's fall. Today, the same instinct persists. Conspiracy forums dissect tetrad dates for hidden messages, while artists and musicians weave them into lyrics and visuals. For skywatchers, the next tetrad in 2032 promises a fresh spectacle and perhaps a calmer reception. By then, the cycle of fear and fascination may have shifted. But one thing's certain, when those 4 blood moons rise, they'll remind us that the sky doesn't just obey physics. It also mirrors our hopes, fears, and endless hunger for meaning in the stars. In January 2023, a ghostly green visitor emerged from the depths of the solar system comet C 2022 E3 ZTF, a cosmic snowball glowing with an otherworldly emerald hue. This wasn't just another blurry speck in a telescope. It was a time capsule from the last ice age, completing its first journey past Earth in 50,000 years. The last time this comet graced our skies, Neanderthals still walked the planet, and early humans were painting mammoths on cave walls. Now it was back, streaking through the constellation Corona Borealis with a vivid green coma, a glowing halo of diatomic carbon vaporizing under the sun's fierce glare. Unlike the pale white or yellow of most comets, this one's eerie color came from a rare chemical reaction. As sunlight broke apart its carbon molecules, they emitted a spectral glow, turning the comet into a celestial neon sign. But spotting this green wanderer wasn't as simple as stepping outside. While it briefly reached naked eye visibility under pristine dark skies, light pollution nearly stole the show for millions. City dwellers saw only a faint smudge through binoculars, if anything at all. The difference between urban and rural views was staggering. In Wyoming's Grand Teton National Park, photographers captured the comet's gossamer tail stretching across the Milky Way, while in downtown Chicago, even experienced astronomers strained to find it. This stark contrast highlighted a growing crisis. Our artificial lights are erasing the night sky. Comets like this one, which rely on subtle contrasts against the dark, are often the first casualties. The comet's rarity added urgency to the chase. With an orbital period of 50 millennia, this was a once-and-done opportunity for everyone alive today. Professional observatories like the Zwicky Transient Facility, the survey that discovered it, tracked its path with precision, while amateur astronomers shared real-time sighting tips online. The best views came in late January when the comet passed closest to Earth, just 26 million miles away. Telescopes revealed its intricate ion tail, a streak of charged particles blown by solar winds like a cosmic windsock, while its broader dust tail curved gently behind, reflecting sunlight in a softer glow. What made this comet especially remarkable was its unpredictability. Unlike Halley's comet or NEOWISE, whose behaviors were somewhat charted, C2022 E3 ZTF was a wild card. Comets are notoriously fickle. Their brightness depends on how much ice they shed as the sun heats them, and this one's activity fluctuated dramatically. Some nights it flared unexpectedly, other times it dimmed, keeping observers on edge. That volatility mirrored a broader truth about comets. They're not just pretty lights in the sky. They're ancient remnants of the solar system's birth, carrying clues about how planets formed and where Earth's water originated. Every close study, whether by telescope or spacecraft, peels back another layer of that mystery. For those who missed the green comet's peak, the lesson lingers. The next 50,000-year visitor might already be drifting toward us from the Oort cloud, a frozen realm at the solar system's edge. And while we can't control celestial timing, we can protect our ability to see these wonders by pushing back against light pollution. Simple fixes, shielding streetlights, using warmer-colored bulbs, or just turning off unnecessary outdoor lights can reclaim the stars for future generations. Because when the next rare comet arrives, whether in our lifetimes or our descendants, it deserves a sky dark enough to let its glow truly shine. In January 2007, a celestial torch blazed across the southern hemisphere. Comet McNaught, the brightest comet since 1965, so luminous it outshone Venus and remained visible even at high noon. This wasn't just another fuzzy streak in a telescope. It was a cosmic bonfire, its fan-shaped tail stretching like a searchlight across 20 degrees of sky. Named after astronomer Robert McNaught, who discovered it the prior year, this icy wanderer transformed from a dim speck near Saturn into a showstopper as it rounded the sun, its ices vaporizing into a dazzling plume of dust and gas. What set McNaught apart wasn't just its brilliance, it was its audacity. Most comets favor the dim backdrop of night, but this one didn't wait for darkness. It flaunted itself in broad daylight, a rare feat achieved only by history's greatest comets like Icosecchi in 1965 or the legendary Great Comet of 1882. The secret to McNaught's spectacle lay in its orbit, a hairpin turn around the sun that brought it within 15 million miles of our star, closer than Mercury. Solar heat ignited its frozen gases, ejecting torrents of dust that reflected sunlight with staggering efficiency. But here's the twist: McNaught's glory was a southern hemisphere exclusive. As the comet swung away from the sun, its tail unfurled like a peacock's feathers over Australasia, South America, and Africa, while northern observers could only read about it in awe. This celestial favoritism wasn't random. Comet orbits tilt at sharp angles to Earth's plane, and McNaught's path angled southward after perihelion, gifting half the planet with front-row seats to a once-in-a-generation show. Comparisons to other great comets reveal just how special McNaught was. Hale-Bopp in 1997 lingered for months but lacked McNaught's daytime audacity. NEOWISE in 2020 dazzled globally but never matched its sheer luminosity. McNaught's tail, a structural masterpiece of separate dust and ion streams, became a laboratory for scientists. The European Space Agency's Ulysses spacecraft accidentally flew through its tail, detecting unexpected chemical complexity, including ions of iron and nickel, metals normally associated with asteroids, not icy comets. This oddity hinted that comets might be more chemically diverse than we thought, blurring the line between rocky and icy solar system bodies. For Southern Hemisphere stargazers, McNaught became a cultural touchstone. In Australia, tourists flocked to remote outback sites, while in New Zealand, Maori astronomers wove its appearance into ancestral narratives. Photographers captured its tail arcing above iconic landmarks: Table Mountain in South Africa, the Andes in Chile, each image a testament to its otherworldly scale. Even city dwellers, usually robbed of celestial wonders by light pollution, could step outside at dusk and gasp at the comet's radiant core and ribbed tail structure, no equipment needed. Yet McNaught's legacy extends beyond its beauty. It taught astronomers that great comets defy easy categorization. Some, like Halley, are famous for their regularity. Others, like McNaught, are one-hit wonders, blasting through the inner solar system on orbits lasting millennia. Its daytime visibility, a trick only possible when a comet's dust production is perfectly aligned with its proximity to both Sun and Earth, remains a rare benchmark. The next comet this bright could arrive next year or not for centuries. For those who missed McNaught, the lesson is clear: comets are cosmic wildcards. They don't follow schedules or care about hemisphere bias. They erupt into glory when their time comes, painting the sky with fleeting, unpredictable strokes. And when the next great comet arrives, whether it favors the north or south, one thing's certain: it'll remind us why humanity has always looked up in wonder. The evening of March 19, 2011, wasn't just another full moon. It was the closest, largest full moon in nearly 2 decades. A celestial illusion so striking that even seasoned skywatchers did double takes. Dubbed the supermoon by an astrologer in the 1970s, the term exploded into popular culture during this event, sparking debates about its true significance. But beyond the hype, the science behind this phenomenon is just as captivating. That night, the moon reached perigee, the closest point in its elliptical orbit around Earth, coming within 221,000 miles of our planet. Compared to its farthest point, apogee, where it drifts out to 252,000 miles, this 26,000-mile difference made the moon appear 14% larger and 30% brighter than usual. What made the 2011 supermoon particularly mesmerizing was its timing. It coincided not just with perigee but with a full moon, creating a perfect storm of lunar grandeur. The human eye plays tricks when the moon hangs low on the horizon, an effect known as the moon illusion, where it appears unnaturally large against trees or buildings. But during perigee, the moon's size increase is real, measurable, and breathtakingly photogenic. Photographers race to capture it looming behind iconic landmarks, from the Statue of Liberty to the Sydney Opera House, using telephoto lenses to exaggerate its scale against earthly backdrops. The key to a stunning supermoon shot: timing your session within minutes of moonrise or moonset, when the low angle enhances atmospheric distortion, adding a warm, dreamy glow to its craters and seas. Yet the supermoon's influence extends beyond aesthetics. Its gravitational pull, strongest at perigee, exerts extra force on Earth's oceans, creating what scientists call perigean spring tides. These aren't your average high tides, they're noticeably higher, sometimes exacerbating coastal flooding when paired with storms. During the 2011 event, regions like the Bay of Fundy in Canada saw tidal surges nearly 20% stronger than usual, while surfers in Australia chased once-in-a-season waves fueled by the moon's proximity. Critics often dismiss supermoons as overhyped, arguing the visual difference is subtle to untrained eyes. But for tide-dependent communities, fishermen, ship captains, even marine biologists tracking coral spawns, these lunar close passes are anything but trivial. The beauty of supermoons lies in their accessibility. Unlike eclipses or meteor showers requiring perfect conditions, anyone can step outside during a perigee full moon and marvel at its amplified glow. The next standout supermoon arrives on November 25, 2034, when the moon swings even closer than in 2011, but you don't have to wait decades for a worthy sighting. Every year brings a few perigee full moons, often 2 or 3 in a row, each offering a fresh chance to witness our celestial neighbor at its most commanding. Whether you're a photographer chasing the perfect shot, a scientist measuring tidal shifts, or simply someone who appreciates a moonlit walk, these lunar close encounters remind us that even familiar objects in the night sky can still surprise us. The moon may be Earth's constant companion, but when it leans in close, it commands attention like nothing else. The summer of 1991 transformed thousands of casual skywatchers into lifelong eclipse chasers, and it all hinged on a celestial illusion. On July 11th, as the moon slid directly in front of the sun, spectators across Hawaii, Mexico, and Central America didn't experience the jaw-dropping totality of a full solar eclipse. Instead, they witnessed something equally hypnotic, a blazing ring of fire framing the moon's silhouette, a phenomenon known as an annular eclipse. Unlike a total eclipse where the moon completely blocks the sun's disk, an annular eclipse occurs when the moon is too far from Earth in its elliptical orbit to fully cover the sun. The result, a perfect circle of sunlight, searing and surreal, encircling the moon like a cosmic wedding band. What made the 1991 event legendary wasn't just its visual drama, it was its role in birthing modern eclipse tourism. Before then, most people associated eclipses with brief totality zones or partial shadows, but this annular eclipse, visible for over 7 minutes along its central path, proved that almost total could be just as captivating. Photographers captured the ring's ethereal glow above Mayan ruins in Mexico, while astronomers noted how the thinner sunlight revealed delicate structures in the sun's corona typically drowned out during total eclipses. The eclipse also showcased a quirky atmospheric effect. As sunlight filtered through gaps in palm leaves or lattice structures, it projected countless miniature rings of fire onto the ground, a natural pinhole camera show that turned sidewalks into art installations. The distinction between annular and total eclipses goes deeper than appearance. During totality, the sun's outer atmosphere, or corona, erupts into view, a shimmering halo of plasma that's invisible otherwise. But annular eclipses, with their persistent ring of sunlight, keep the corona hidden. Instead, they offer a unique chance to observe the sun's limb darkening, where the edges of the solar disk appear dimmer than the center due to the sun's gaseous composition. This subtle gradient, normally lost in the sun's glare, becomes strikingly obvious during the ring's formation. Upcoming annular eclipses, like the one crossing the Americas on October 14, 2023, will give a new generation of viewers front row seats to these nuances, provided they're standing under the narrow path of annularity. For those planning to chase the next ring of fire, timing and location are everything. The 2023 eclipse will carve a path from Oregon to Texas before sweeping across Central America, while 2024's annular eclipse will grace southern Chile and Argentina. Unlike total eclipses, where the brief darkness demands perfect alignment, annular eclipses allow more flexibility. Their extended visibility window, often over 10 minutes, means you can enjoy the spectacle without frantic last-minute travel. But don't settle for a partial view outside the central path. The difference between seeing 99% coverage and the full ring is like comparing a campfire to a bonfire. Only those directly under the moon's shadow will witness the fiery loop in its full glory. What keeps eclipse chasers coming back to annular events, even after experiencing totality's awe? It's the sheer improbability of the geometry. Total eclipses require the moon to perfectly mask the sun, a coincidence possible only because the sun is 400 times larger than the moon and 400 times farther away. Annular eclipses, by contrast, highlight the moon's ever-changing distance from Earth, a reminder that celestial motions are never static. When you stand under that ring of fire, you're witnessing a precise moment in an orbital dance that's been unfolding for billions of years, a dance where even a few thousand miles in the moon's orbit can turn totality into a golden halo. Whether it's your first eclipse or your 50th, that ring never loses its power to make the universe feel intimately, breathtakingly close. On April 9, 2005, the universe screamed a pulse of energy so violent it briefly outshone every star in the observable cosmos. In a fraction of a second, GRB 050509b unleashed more power than our Sun will produce in its entire 10 billion-year lifetime. But here's the staggering part. This gamma-ray burst, the most distant visible explosion ever recorded at the time, had been traveling for 13 billion years before reaching Earth. Imagine a light bulb flickering at the dawn of time, its glow only now piercing the darkness to reach us. This wasn't just a cosmic firework, it was a death cry from the universe's infancy, a relic from when galaxies were newborns and the first stars were still fusing hydrogen into heavier elements. Gamma-ray bursts like this one are the universe's most catastrophic events, born from collapsing hypergiant stars or colliding neutron stars. When a massive star exhausts its fuel, its core collapses into a black hole, triggering twin jets of plasma that drill through the star at nearly light speed. These jets, hotter than a billion suns, punch into space as gamma rays, the most energetic form of light. GRB 050509b's journey stretched so far that its light predates Earth itself, emitted when the universe was just 700 million years old. Had this explosion occurred within our galaxy, even thousands of light years away, the gamma rays could have sterilized entire planets. Instead, its redshifted whispers offered astronomers a time capsule from the cosmic dark ages. What makes these bursts so thrilling for amateur astronomers? Unlike supernovas or comets, you don't need a telescope to detect them, just the right tools and a bit of luck. Gamma rays are invisible to human eyes, but their afterglows often linger in visible light for hours or even days. Automated networks like the Gamma Ray Burst Coordinates Network alert stargazers worldwide within seconds of a burst's detection by satellites like NASA's Swift Observatory. Enthusiasts with modest telescopes can then pivot to the coordinates, capturing the fading embers of these cosmic catastrophes. In 2022, amateurs in New Zealand photographed the afterglow of GRB 220427 a mere minutes after the alert, their images contributing to real-time scientific analysis. The hunt for gamma-ray bursts is part treasure chase, part time travel. Each detection peels back layers of cosmic history, revealing how heavy elements like gold and platinum were forged in stellar furnaces. GRB 050509b's extreme distance forced scientists to rethink early universe models, proving that massive stars lived and died violently far sooner after the Big Bang than previously thought. And while we'll never see that specific burst again, new ones flash across the sky weekly, each carrying secrets from distant corners of spacetime, so keep your eyes on the alerts. The next cosmic scream could arrive tonight, a billion-year-old message waiting to rewrite what we know about the universe's fiercest explosions. The morning of April 10, 2019, didn't just mark another day in astronomy, it shattered our understanding of the cosmos in a single, grainy image. For the first time in human history, we laid eyes on the unseeable, Pauahi, the supermassive black hole at the heart of galaxy M87, its shadow cast against a swirling disk of superheated gas. This wasn't an artist's rendering or a computer simulation. It was a photograph, a feat once deemed impossible since black holes trap even light itself. The Event Horizon Telescope, a planet-sized array linking observatories from Hawaii to the South Pole, had achieved the equivalent of spotting a donut on the Moon's surface from Earth, resolving details smaller than a single light day across 55 million light-years of space. The engineering behind this image bordered on wizardry. To capture Pauahi's shadow, the EHT didn't use a traditional telescope. Instead, it combined signals from 8 radio telescopes across 4 continents, synchronized by atomic clocks precise to within 1 second every 100 million years. This technique, called very long baseline interferometry, effectively created a virtual dish as wide as Earth itself, a necessity since black holes are so compact that observing them requires staggering resolution. For M87's black hole, 6.5 billion times more massive than our Sun, that meant detecting subtle variations in radio waves emitted by gas molecules spiraling toward oblivion at near light speeds. The resulting image, processed over 2 years by supercomputers crunching petabytes of data, revealed the black hole's photon ring, a perfect circle of warped spacetime where light orbits like a car on a cosmic racetrack before plunging inward. But the real magic lay in how this blurry orange donut confirmed Einstein's century-old predictions. General relativity had long suggested black holes would cast circular shadows, but until 2019, no one knew if reality would match theory, especially under such extreme gravity. The near-perfect symmetry of Pauahi's shadow proved Einstein right yet again, while its slight asymmetry hinted at the black hole's spin, a clue to how it devours matter and launches jets of plasma stretching thousands of light-years. For astronomers, this wasn't just a pretty picture. It was a Rosetta Stone for decoding how black holes shape galaxies, bending the very fabric of the universe around them. Now, the EHT has set its sights on an even more tantalizing target, Sagittarius A star, the supermassive black hole lurking at the Milky Way's core. Just 27,000 light-years away, a stone's throw by cosmic standards, it's 1,000 times less massive than Pauahi but far more dynamic, flickering with X-ray flares as it nibbles on passing stars and gas clouds. Capturing its image presents new challenges. Where M87's black hole appeared relatively stable over days, Sagittarius A star changes by the hour, requiring algorithms that can stitch together snapshots like a celestial flipbook. And because it's shrouded by interstellar dust, observing it demands shorter wavelengths that pierce through the haze, a technical hurdle the EHT is tackling by adding new telescopes to its network. What's next for black hole photography? The EHT plans to go cinematic, creating videos of these gravitational monsters in action. Future expansions could include space-based radio telescopes, boosting resolution enough to spot the hotspots theorized to whirl around black holes at relativistic speeds. Every new image will peel back another layer of mystery, testing whether black holes truly obey relativity's rules or if, at their very edges, new physics awaits discovery. When you look at that 2019 image, a fuzzy halo framing cosmic nothingness, you're not just seeing a black hole, you're witnessing the edge of human ingenuity, where science transforms the unimaginable into something we can hold, share, and marvel at together. On September 26, 2022, humanity took its first deliberate step toward becoming an interplanetary defense force, and the target was a harmless space rock named Dimorphos. NASA DART mission, short for Double Asteroid Redirection Test, wasn't just another scientific experiment. It was a cosmic billiard shot, a spacecraft the size of a vending machine slamming into an asteroid at 14,000 miles per hour to nudge it off course. The goal, to prove we could deflect a hazardous asteroid before it ever reached Earth. For centuries, we've been sitting ducks in a celestial shooting gallery, but this mission marked the moment we finally reached out and pushed back. What made DART so groundbreaking wasn't the impact itself, it was the precision. Dimorphos, a 500-foot-wide moonlet orbiting the larger asteroid Didymos, was chosen because it posed no real threat to Earth. This was a controlled test, a way to measure how much kinetic force could alter an asteroid's trajectory. The spacecraft's onboard camera streamed live images up to the final second, revealing Dimorphos's rubble pile surface in startling detail before the signal cut out. But the real drama unfolded in the weeks that followed. Telescopes around the world, from amateur backyard rigs to the Hubble Space Telescope, turned their gaze toward the Didymos system, watching for changes. The results stunned even the most optimistic scientists. DART had shortened Dimorphos's orbit by a staggering 32 minutes, far more than the predicted 73 seconds. The asteroid hadn't just been nudged, it had been dramatically reshaped, with debris from the impact forming a comet-like tail stretching thousands of miles into space. For amateur astronomers, tracking the aftermath became a thrilling challenge. While Dimorphos itself is too faint to see without professional-grade optics, its orbital dance with Didymos created measurable brightness dips that backyard telescopes could detect. Online communities shared timetables for these mutual events, moments when one asteroid passed in front of the other, casting a shadow observable from Earth. By noting how these timings shifted post-impact, even hobbyists contributed to understanding DART long-term effects. Meanwhile, Hubble and the James Webb Space Telescope captured the debris plume evolving in real time, revealing how solar radiation pressure sculpted the ejected material into intricate patterns like smoke rings blown by cosmic wind. The implications stretch far beyond this one test. DART proved that deflection isn't just science fiction, it's a viable strategy, at least for smaller asteroids. Missions like ESA's upcoming Hera, set to visit Dimorphos in 2026, will study the crater left by DART and measure the asteroid's altered mass distribution. But the real lesson is broader. Humanity no longer has to fear asteroids as inevitable doom. With enough warning time, something projects like the Vera Rubin Observatory are designed to provide, we could one day replicate DART's success on an actual threat. The universe might still throw rocks at us, but for the first time in history, we've shown we can throw back. From the fleeting brilliance of daylight fireballs to the slow, majestic dance of planets aligning across millennia, the universe offers a spectacle for every kind of skywatcher. Some events, like a supermoon or a meteor shower, reward those who simply step outside and look up. Others, like the once-in-50,000-year passage of a green comet or the razor-thin path of a total solar eclipse, demand planning, travel, and a bit of luck. But that's the magic of astronomy. Whether you're watching Jupiter's moons through a backyard telescope or lying on a hillside as the Perseids streak overhead, the cosmos meets you where you are. What ties these events together isn't just their rarity, it's the way they dissolve time. When you witness Halley's comet, you're sharing the same view as Mark Twain and medieval scribes. When you chart Mercury's transit, you're using the same celestial mechanics that revealed the scale of the solar system to 18th century explorers. Even the most cutting-edge phenomena like black hole photographs or asteroid deflection tests connect to humanity's oldest questions: where do we come from? Are we alone, and what's out there waiting to be discovered? So how do you prepare for these moments? Start simple. A pair of binoculars can reveal Jupiter's cloud bands or the craters on the moon. Free apps like Stellarium or Sky Safari turn your phone into a pocket planetarium, guiding you to upcoming eclipses, planetary conjunctions, or meteor showers. For deeper immersion, local astronomy clubs offer star parties where seasoned observers share their telescopes and their expertise. And when a once-in-a-lifetime event like the next great American eclipse arrives, don't just watch it online. Stand in the shadow, feel the temperature drop. Let the universe remind you that you're part of something far grander than daily life suggests. The sky isn't a static painting. It's a living, evolving theater, and every rare event is an invitation to look deeper. Maybe you'll chase the ghostly glow of the northern lights or train your lens on Saturn's rings during opposition. Perhaps you'll set an alarm for the next blood moon or join the global vigil for Betelgeuse's inevitable supernova. Whatever catches your eye, remember this: the universe doesn't keep a schedule. It offers these moments freely, but only to those who bother to look up. Now it's your turn. Which celestial event has you counting down the days? Is it the 2024 total solar eclipse, the return of Halley's comet in 2061, or something we haven't even predicted yet? Drop your answer below, and may your skies stay clear, your curiosity boundless, and your sense of wonder forever alive.